Greetings, everyone. Learning as a hobby here. I want to finally finish up chapter 4 today with the solution set to, or the exercise set to section 4.4 in Tao's Analysis 1 book. So let me bring up my solutions. We'll go through it. This is a short exercise set. So again, this video will be kind of short itself. But let's stop talking and get through it. So question number 1 says prove proposition 4.4.1. He gives a hint, so let me actually remind you what proposition 4.4.1 says, and then I'll show you the proposition that he's referring to here in the hint. So the proposition we're going to prove in this question is this one, interspersing of integers by rationals. Let x be a rational number, then there exists an integer n such that n less than equal x less than n plus 1. In fact, this integer is unique. He's just explaining what that means. In particular, there exists a natural number n such that n greater than x. So there's no such thing as a rational number which is larger than than all the natural numbers. Okay, and then the proposition, so here in the hint he says use proposition 239. That's the Euclidean division lemma back from chapter 2, which is this one here. Let n be a natural number and let q be a positive number. Then there exists natural numbers m and r such that 0 less than equal r less than q and n equals mq plus r. So that's what we're going to use to do this one. So here I'm going to in order to use that lemma, I'm going to take the absolute value of an arbitrary rational number here because we're guaranteed that that's always non-negative. So let x be a rational number, then absolute value x is also rational, and furthermore, it's greater than or equal to 0, or in other words, it's non-negative. Then there exists pq, natural numbers, such that p is greater than 0, q is greater than 0, such that the absolute value of x is p over q. Then there are nr, natural numbers such that p is nq plus r, where r is greater than or equal to 0 and less than q. This is just, again, by just proposition 2.3.9. Right? Then here, starting from this inequality, you can add nq to all three sides, and that gives you nq is less than or equal to nq plus r, less than or equal to nq plus q, which nq plus r you can replace with p, and you can factor out the q on the right-hand side, and that gives you n plus 1 times q, which is the inequality that we wanted, because p over q is equal to x. So you could divide, in other words, you can divide everything by q. All right, so that shows the existence, and now we have to also show uniqueness. So assume that there are mn natural numbers such that n less than or equal absolute x less than n plus 1, and also m less than or equal to absolute x less than m plus 1. Then without loss of generality, we can assume that m is less than n, then m plus 1 less than n plus 1 by the order properties of natural numbers. That implies m is less than n is less than m plus 1, which implies that the successor of m is less than or equal to n by proposition 2.2.12 part E, if you look back in chapter 2. And that implies that m plus 1 is less than or equal to n. I'll explain that star in a second, which contradicts that n is less than m plus 1. Therefore, m has to be equal to n. The natural numbers n such that that whole thing there implies that the natural numbers n such that n less than or equal to absolute value x less than n plus 1 are unique. All right, the star here is just, I did prove this in chapter 2, but he doesn't actually state it as a theorem or a numbered theorem or proposition in chapter 2. It's something he asks you in, like, just as an aside to say, he says, why is this true? So actually I proved it back then, but just to remind you, because I can't refer back to a numbered proposition, this is the proof that the successor of m is equal to m plus 1. So the successor of 0 is defined to be equal to 1. And if you add m to both sides of that equation, then equality is preserved. So m plus the successor of 0 is equal to m plus 1. And m plus the successor of 0 is the same thing as m plus 0. The successor of m plus 0 by definition, but m plus 0 is equal to m. So m plus 0, the successor of m plus 0 is the successor of m. And that shows that the successor of m is equal to m plus 1. Okay, that's basically the proof of 4.4.1. Next, we go on to question 4.4.2. He starts out with a definition. He says a sequence A0, A1, A2, dot, 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 of numbers, by which we mean either natural numbers or integers or rationals or reals, is said to be in infinite descent if we have an greater than an plus 1 for all natural numbers n. In other words, A0 is greater than A1, is greater than A2, et cetera, et cetera. Okay, and then there's two parts to this. Part A says, prove the principle of infinite descent, which he's giving us here, that it is not possible to have a sequence of natural numbers, which is an infinite descent. And he gives a hint on how to do this. He says, assume for the sake of contradiction that you can find a sequence of natural numbers, which is an infinite descent. Since all the an are natural numbers, you know that an is greater than or equal to 0 for all n. Now use induction to show, in fact, that an is greater than or equal to k for all natural numbers k and all natural numbers n, and obtain a contradiction. So I just followed his hint. So assume that A0, A1, A2, dot, dot, dot is a sequence of natural numbers in infinite descent. Then here's the claim. An is greater than or equal to k for all k in n and all n in n. So here we'll do this by induction, and we're going to induct on k for this problem. So start with your base step, k equals 0. An is a natural number for each n in n, which implies that an is greater than or equal to 0, right? Because 0 is less than or equal to every natural number. All right, then we go on to the inductive step. Assume there is a natural number k such that an greater than or equal to k for all natural numbers n. Then assume k plus 1 is greater than ai for some I in n, so for some natural number I. For the sake of contradiction, then k is less than or equal to am is less than k plus 1 for all m greater than or equal to I, which implies that 0 is less than or equal to am minus k, which is less than 1 for all m greater than or equal to I, which implies that the successor of am minus k is equal to am minus k plus 1, which is less than or equal to 1, which implies am is less than or equal to k for all m greater than or equal to I, which implies that am plus 1 less than am less than or equal to k, and that contradicts the inductive hypothesis. Therefore, an must be greater than or equal to k plus 1 for all natural numbers n. And that shows that an is greater than every natural number for for all terms in the sequence. So the above property contradicts that A0, A1, dot, dot, dot is a sequence of natural numbers in infinite descent, since if the sequence is in infinite descent, then A1 is less than A0, for example. However, by the above property, since A1 is a natural number, that means that A0 is less than or equal to A1, and that's your contradiction. So that proves that the principle of infinite descent is true. All right, part B is actually pretty quick. Here, he just asks a couple of questions that can be explained with some counter examples. So does the principle of infinite descent work if the sequence A1, A2, A3, dot, dot, dot is allowed to take integer values instead of natural number values? And then he asks also, what if it is allowed to take positive rational values instead of natural numbers? And he wants us to explain. The answer to both of those questions is no. And here are two counter examples. So for example, part 1, the sequence n minus 1, where n goes from 0 to infinity, is a sequence of integers that are in infinite descent. And part 2, this is a sequence of positive rational numbers that are in infinite descent, so 1 over n, where n goes from 1 to infinity. All right, so that shows that these two questions are false. The answer to them is that they're false. Okay, and then there's this last question. Like I said, it's a pretty short exercise set. Here he wants us to prove proposition 4.4.4. Let me just remind you of what that says. Here it is. There does not exist any rational number x for which x squared is 2. All right, so actually what he asks us to do in the exercise set is to prove the statements that he asks why about in the proof that he actually does in the book. So actually he sketches the proof for this in the book, but he makes some statements that he asks the reader to prove in the exercise set. So I'll prove those statements first, and then I'll show you his proof, and then we'll just refer back to the lemmas that we need when we get to those parts. All right, so here's my proof. We introduce some preliminary results first before tackling the proof itself. So first thing is a definition. Let P be a natural number. We say P is even if there is a natural number k such that p is 2k. We say p is odd if there's a natural number k such that p equals 2k plus 1. All right, and then here's the first lemma that we need. Every natural number is either even or odd, but not both. Right, so here's my proof. The fact that every natural number is either even or odd follows from proposition 2.3.9, which is the Euclidean division lemma. So we can go from existence now to showing that you can't have both even and odd. Assume for the sake of contradiction that there is a natural number p that is both even and odd, then there are km natural numbers such that p is 2k equals 2m plus 1. Then 2 times k minus m is equal to 1, which implies that k minus m is an integer, is a natural number, and also that k minus m is positive, which implies that k minus m is greater than or equal to 1. Multiplying that inequality through by 2 preserves the order relation, which implies that 2 times k minus m is greater than or equal to 2, but 2 times k minus m is equal to 1, so that shows that 1 is greater than or equal to 2, which of course is a contradiction. Therefore, every natural number is either even or odd, but not both. All right, here's another lemma that we need. Actually, what we need is the contrapositive of this, but you hopefully you know how to form the contrapositive. But anyway, here's lemma 2. Let p be a natural number. If p is odd, then p squared is odd. And here's the proof. Let p be an odd natural number. Then p equals 2n plus 1 for some natural number n. Then p squared equals 2n plus 1 squared, which equals to 2 times 2n squared plus 2n plus 1. And we know that 2n squared plus 2n is a natural number. Therefore, p squared is 2m plus 1 for some natural number m, which in this case happens to be 2n squared plus 2n, which implies that p squared is odd. So what we need is actually the contrapositive of this, the contrapositive of this, which states that p squared even implies p is even. Right, and then here we need this other last lemma here before we can get to the proof. Lemma 3 says let pq be non-zero natural numbers. If p squared equals 2 squared, then q is less than p. So here's the proof. Let pq be such natural numbers, right? Positive natural numbers, such that p squared equals 2q squared. Assume for the sake of contradiction that q is greater than or equal to p, then q greater than 0, p greater than 0 implies q squared greater than p squared, which implies that p squared equals 2q squared greater than or equal to 2p squared greater than p squared. And that's a contradiction because p squared can't be greater than p squared. Therefore, q is less than p. All right, and then here's the proposition. Like I said, he actually does this in the book, but now we have the lemmas that we need proved, so we can just go through the proof completely. So assume for the let me just restate the proposition. Square root 2 is not a rational number. So assume for the sake of contradiction that square root 2 is rational, then there are natural numbers p and q greater than 0, such that square root 2 equals p over q. Clearly p is not 0, since if you squared 0 over q, you get 0 squared, which is 0. Also, we can assume p is positive, since if p is negative, then we can take negative x, which would be positive, and notice that negative x squared is the same thing as x squared. Then, since square root 2 is equal to p over q, by our assumption, then 2 is p squared over q squared, which means that 2q squared equals p squared, which implies p squared is even, which means that p is even by lemma 1 and lemma 2, the contrapositive of it. But then p equals 2k for some positive natural number, which implies p squared equals 2k squared. Which is when you simplify 4k squared equals 2k squared, which implies that by cancellation implies 2k squared equals q squared. Now we know already that q is less than p, and p squared equals 2q squared, and also k is less than q, and 2k squared equals q squared. By this, that follows from lemma 3. This process can be continued ad infinitum, constructing solutions xy of non-negative integers that are solutions to 2x squared equals y squared that form a sequence of natural numbers in infinite descent. And this contradicts the solution that we just talked about in exercise 4.4.2. And that proves the theorem. Okay, and that's it. Like I said, kind of short. But what that means is that we're done with chapter 4. So now we can finally move on to the construction of the real numbers, which is great. I was hoping to finish the construction of the real numbers before the end of the summer. It looks like we're on schedule to do that. So the next video I think I'm going to do is a vlog for my vlog for August. So look out for that. But then we'll start on chapter 5. So I'll see you guys in the next one. Let me know what you think down below. Give me a like and subscribe if you enjoy the content, and I'll see you guys in the next video.